Very good afternoon, everyone. Professor Taichiro, am I audible to you?
I hope my voice is coming through today.
Sir, I think you're on mute.
Oh, okay, let me try this again.
We'll start the meeting we'll start the webinar in 2 minutes. We'll just wait for any other participants if they have to join us.
Okay. So how's my microphone working?
It's
Okay.
working perfectly fine.
Okay, thank you.
Hello everyone. I am Devyani, and on behalf of Structural Steel Education Forum, I would again like to welcome you all to our third webinar and part 2 on steel buildings in Japan, fabrication and construction, to be delivered by Professor Taichiro Okazaki. And for our participants who've joined us this time, I would like to introduce Dr. Okazaki is a professor of structural engineering at the Division of Architecture at Hokkaido University. He holds a BE and ME in architecture and architectural engineering from Kyoto University. He received his Ph.D. in civil engineering in 2004 from University of Texas at Austin, USA. Prior to his appointment at Hokkaido University in January 2011, he was a researcher at the National Research Center for Earth Sciences and Disaster Prevention of Japan and assistant professor at the University of Minnesota, USA. Dr. Okazaki's research and teachings interests are in behavior of steel structures, structural mechanics, and earthquake engineering. Dr. Okazaki is a member of professional societies, including Architectural Institute of Japan, the Japan Association for Earthquake Engineering, American Society of Civil Engineers, and American Institute of Steel Structures. Since 2021, he serves as associate editor of the Journal of Earthquake Engineering. If any participants have any questions during the session, they may leave them in the comment box, and Professor shall answer them at the end of his talk. With this, sir, I would like to hand over the stage to you to begin your presentation.
Okay, thank you very much, Devyani, for your nice introduction again. Good evening. My name is Taichiro Okazaki. Let me start. Wait a minute. I realized. Wait a minute. Sorry. This is it. I'm a little confused with what I have on screen, but I think I've identified it. This one. This one. Okay. Do you see on the screen my presentation? I hope it's working.
Yes, sir, it's visible.
Yes. Thank you, Devyani. Again, good evening, good afternoon. My name is Taichiro Okazaki. Today, I will deliver the part 2 of what I was of my presentation on steel buildings in Japan. This part 2 is going to be more on execution. Okay. The outline of today's lecture is going to be first going through components of steel buildings as they are constructed in Japan. An overview of how the steel building comes together. Then third, just a little emphasis on the availability of steel in Japan. Then moving on to the second half, a mention of what items there are in quality control. And the core of today's discussion are how steel are fabricated and then erected to form a building in ordinary buildings and then in high-rise buildings. I will conclude with a short summary. Now, let's begin by explaining the components of a steel building as they are constructed in Japan. And this is an illustration of a steel framing system with the floor. But looking at this at the side, remembering that a steel building comprises the primary load resisting members, which are the columns, beams, floor beams, the diagonal or horizontal braces. This is what we call the structure. This is what we see, the primary items that we would be designing. But steel buildings do not stand by steel alone. There is the reinforced concrete foundation, and the concretes or the floors are typically formed by reinforced concrete. We need to complete the skin of the structure with some external cladding, or in some cases glazing. We have the partition walls to form rooms. We have a variety of internal finishes, ceilings, equipment, and furniture and fixtures. Now, what I show here in dark color are typically, at least in the academic realm, called non-structural components. But today, let me focus on the structural system. Okay, let me try to get. Okay, the structural system comprises columns, which might be spliced vertically. We have the girders connecting the columns. Floor beams that are supported by girders, and these long girders and floor beams may be braced laterally by sub-beams. On top of these girders and floor beams, we will have metal decks connected through shear studs. Let's look at a real building example. This is a building, a rather high-rise building under construction. This is what the beams and columns would look like in that particular building. The beams are the I-section beams or the girders are connected to hollow square columns, and the beam flanges are welded to the column, and the web is bolted to the column. Later in today's lecture, I will go through the arrangement of these connections. And on top of the girders, we see the metal deck, and supposedly on top of the metal deck, there will be reinforced concrete cast on top. We have these kicker braces for the girders and some piping going through. Also, you may be wondering what these holes are. Yes, they are for the equipment and piping to go through, and they are typically stiffened or reinforced. Right in this example, I think I identify a ring welded to reinforce the hole. A different floor. This seems to be an equipment floor with a lot of bracing, maybe outriggers or otherwise supporting something heavy above. You may notice that in Japanese steel construction, we use a lot of bolts in addition to lots of welds. Hey, looking at the floor from below and above, the photo below looks at the metal deck right before the concrete is being cast. There's the minimum reinforcement for temperature control. Okay, this is not a very ideal photo, but you see shear studs penetrating the metal decks for secondary or floor beams, but the primary beams in Japan never have the shear studs penetrating the deck. The shear studs, small in this photo, are seen here. They are welded directly on the top flange. And the metal decking is tack welded to this flange, not to entirely cover the top flange of the beam. Now, the typical steel products used in steel buildings are these. The columns in Japan are typically square HSS or hollow structural shapes. The beams are I sections. We heavily use corrugated metal decks, and most other sections are for supplementary items. Now, looking in some of the connections on the photo actually, let's work from the top photo. Typically in Japan, I think this is a construction 7-8 years ago, so these days it's a little different, but we see fireproofing in the form of foam. These days it's more common to use wrapping material for fire protection. This floor, the equipment in the ceiling is nearly done, so we see a lot of duct running through the structurally supposedly important girders. In the bottom photo, we see a column being spliced. And you might notice that these white objects that are long vertically, these are the external claddings that are supported on the bottom side at the concrete slab, and probably on the top side by the beam. Now, let's quickly go through how such steel buildings are constructed. Okay, this is an enlarged photo of the same building. This is the building after completion. Let me flip back again. I'm going to repeat this a couple of times for different buildings. This is what I saw during construction, some of the structural system exposed. And today it looks like this. Another steel building. This one was quite peculiar because there's a long span with no columns on the left side, and on the right side, right-hand side, there's a short span with some device for energy dissipation. Okay. And this building today looks like this. This is a television broadcast station, and that long column-free floor area was probably for office space. And that shorter span become probably staircases and equipment and such. Another building, this went up last year. From the photo on the right-hand side, you may not think this to be a steel building, but it actually is. On the left-hand side, you see the steel going up as the cladding is being attached. Now, one of today's important message is that typically in Japan, we favor constructing these column trees in the fabrication shop, so that much of the important welds are completed in the controlled environment. Bring these column trees, connect them vertically in the construction site, while connect the columns horizontally by intermediate pieces of the beam. This way, we can complete the critical welds in the controlled environment, and in the construction site, we can do much of the erection work by bolting. We do weld in this fabrication shop as in the field. And there's roughly two different types of construction in Japan. One is to form the column tree that I mentioned. Complete the column with short beam stubs. The photo in the top shows the beam to column connection area being welded together. And the intermediate part of the column would be inserted over stories to form a long column tree. Okay, this construction scheme on the left-hand side is favored for the reasons that I mentioned, I've been mentioning, so that the critical welds could be done in the fabrication shop. But when we have to, we will do a field welding. Now, field welding in Japan, I believe India would be similar. Japan is a windy and rainy environment. Actually, in the summer, it's very damp. The weld environment has to be protected, and the welder needs to be provided good footing to do good work. The standard footing device is used for the welder as well as the inspector. Now, this left-hand side is favored, and we do this as much as possible. But when the columns and beams become too big, we need to give up and resort to the construction I'm showing on the right-hand side, which uses more welding in the field. Either way, the primary welds in Japan are done by gas shielded metal arc welding. Okay, so this is the more favored type of construction. The welds involved would be the welds to insert these thick diaphragm plates through the column. Why do we need this? This is because if you would weld the flange of the beam directly to the column, the compression or tension delivered to the column would distort the tubular shape of the column. So this, what we call this diaphragm plate, is the stiffener to stiffen the section and also to allow smooth force transfer between the beam and the column. We need such diaphragm plates at the top, at the level of the top flange of the beam and the bottom flange of the beam. We need to insert two diaphragm plates at each beam. And this diaphragm plate requires CJP groove weld at both sides of this plate. And that's already a lot of welding. And once this diaphragm plate is inserted, we connect this beam stub to this diaphragm plate. The beam flange by CJP groove weld and the beam web by double-sided fillet welds. We construct this column tree in the fabrication shop. We bring it to the construction site, and we connect this column to the adjacent column horizontally by this intermediate beam connected by bolts, many high-strength bolts. Now, this construction of the column tree requires a lot of welding. There is a lot of manual welding done, but to the extent possible, we use robots. Oh, this is one of the reasons we don't mind using HSS or hollow structural shapes. It is because for robots, if you rotate the column gradually, placing or finding the groove and running the torch is not all that bad, because you have this column going circle and circle and circle. Now, when you have big columns and big girders, as in high-rise buildings, we do something different. The columns would be so big such that they needed to be welded from 4 thick plates. The 4 plates will be welded together by very big welding. And even if we form the square hollow shape with thick plates, we cannot avoid that issue of the beam flange distorting the column section. We need a stiffener, but in this case, rather than cutting the column, we have the opportunity to insert the stiffener plate inside in the process of forming this welded built-up column. Now, this type of connection we tend to call the interior diaphragm connection. Instead of having the diaphragm plate protruding the column, we welded inside this square hollow shape. Now, in this case, we can have the shear stab connected to the column, but we will have the beam directly welded to the column in the construction site. This flag indicates welding in the field. The bottom and top flanges will be connected to the column by CJP groove welds. The beam web will be connected to the column through this shear stub and high-strength bolts. Okay, so to form these heavy built-up columns, especially, we use very special welds, submerged arc welding and electroslag welding. I'll talk about this a little later. Now, let me move on to the third subject. Because I think this is important to understand the Japanese steel construction. There's overlap with what I discussed last time, but let me go through the types of steel available in Japan. This is the same diagram I showed. These are the steel sections, but they may be categorized by the way they are made. There are the hot rolled shapes, and there are the cold formed shapes and the light gauge shapes. Now, for beams and girders, we use I sections. For columns, we use these hollow tubular sections, especially the square shapes. But these are cold formed from plates. Now, the steel approved or allowed, permitted for use in buildings are specified by our building standard law. And the building standard law says that there's this industry standard steel. Now, but this building standard law was established in 1980s, and since then there has been newer and better steel made available to the market. Those have not been implemented in the law, but instead they are approved per company, per factory by the Minister of our construction. So I mentioned this last time. In Japan, there is this the industry standard steel and the minister approved steel. It's a peculiar arrangement probably, and we have a variety of steel, but the primary ones are this SS steel, SM steel, and SN steel. These steel grades are for hot rolled shapes and plates. Now, we also have the other category, minister approved steel, which tends to be more special, but for columns, we use this BCR and BCP. These are formed from, flipping back one page, this SN steel, which is the primary structural steel we have available today, but because they are cold form, they are categorized separately. Hey, these are essentially the same as SN steel. So looking at the types of steel available in Japan, we have a big variety, but the primary ones are here. And among the primary ones, the really primary ones I highlight in yellow. Now, I compare this against what is used in the US or the UN. I'm not very familiar with what's done in Europe. And anyway, Europe doesn't do much seismic steel design. So comparing against what's done in the US, to my knowledge, in the US, they almost always use this A992 steel, which has the strength grade of 345 for yield and 448 for tension or for tensile strength. Looking at what we have in Japan, the grade is somewhat lower, but this 490 grade is not too different. So what we use in Japan is not too different from the US, but anyway, we have a variety available in the market. We do have stronger grades, and the stronger grades are used for high-rise buildings. Now, let me walk you through the type of I sections we have. We have this shallow sections and the deep sections and the intermediate sections. Naturally, the shallow ones are more suited for columns. The deeper ones are more suited for beams. Now, aside from standard shapes, we have plate girders and welded shapes. Oh, if you decide to weld together, you can do anything. But if you make a customary shape, it tends to be more expensive than going to the rolled shapes that are available in abundance. Now, another unique variety that we have in Japan is the beams with constant D. What is D? D is this dimension, the out-to-out depth dimension of the beam. What I'm saying, what I'm trying to communicate here is that usually, if you go look at I sections of the same depth category, the H or the flat portion depth is kept constant, and if you make the flange thicker, then the outside dimension what tends to grow. That is for convenience in manufacturing, because that would require less replacement of rollers. Now, however, in Japan, there's a huge variety of steel which keep the D dimension constant and have the H adjusted. Now, this goes from 500, 600, 700, 800, 900, and 1 meter in depth. So we have something like 20 beam sections available at the depth of 1 meter. All that combined, I'm comparing the I sections available in the market in Japan, US, and Europe. Now, looking at Japan, the sections I'm showing in blue are the conventional, the industry standard shapes. I'm plotting the moment of inertia against the area. So sections that have big area but not very substantial moment of inertia are the shallow sections that represent columns. The not so heavy but very big in moment inertia, those are the beam sections. So these that I'm highlighting now would be the columns, and these would be the beams. Now, one thing I want to emphasize in this slide is that in Japan, we have hundreds of these constant D that I mentioned. Engineers have a lot of options for beams. Now, compared to what's available in Japan, even the US, the variety is fewer. They roll shapes from shallow to heavy to intermediate, but the variety is much more dense in Japan. And if you look at Europe, where the steel construction market is probably much smaller than the US, the variety is fewer. But I believe what they do in Europe is that they would import the American steel if they ever need something heavier. Now, you may be worried that in Japan we don't have many variety for columns, but that's wrong. Because we commonly do not use I sections for columns. We use square HSS. So let me keep the US and Europe chart as it is and replace this figure for Japan by what's available for square HSS. And that's this. For US and Europe, I'm showing the available I sections. And for Japan, I'm showing the available square HSS. Now, only looking at the HSS, we have tremendous variety. Now, the reason I'm emphasizing this is that I hear from my international colleagues one of the reasons that steel is not very common in their country or area is because of the few availability of variety. Even in Europe, the variety is much fewer than what's available in the US. Now, even compared to the US, the variety available in Japan for beams and columns is quite a lot. Oh, this is one of the area where our industry have placed a lot of effort. If there's more variety, the engineers can come up with more economical solutions so that steel buildings become a more feasible option. Now, moving on to the next subject, a little bit on quality control. I will talk more about quality control in the last part, but let me try to summarize first before going in there. I mentioned the abundant variety of steel grade. The abundance is in dimension, but also in grade. Now, any fabricator in Japan has this chart. Because if you have steel delivered, by the appearance, it's impossible to distinguish what grade of steel it is. You can tell the shape or the dimension, but not the grade, especially when they are cut, when they're cut plates like this. The distinction is made in two ways. One, we have marking for big sections. Second, especially for plates, we rely on the chart. It says that, for example, these plates have one yellow stripe marking. That means it's this SM490 type A. The thin plates here has one white stripe. That means that it is the SS400. So any fabricator in Japan has this marking, and any stocking company would adopt this marking system. Fabricators are required, and engineers are also required to receive the mill test report to confirm that the delivered steel complies to the standard. In this case, the mill test report says that this qualifies for Japanese industry standard SS400 steel. And in the same heat, they produce this much, but the one I'm handing you now is the one that I stamped here. This is a plate. of a 36 millimeter thick. Okay, it gives the tensile properties and the chemical composition. And looking at these numbers, you can check whether, these numbers are the proof that the steel qualifies the industry standard requirement. The mill test report needs to identify the name of the company and the name of the particular factory or the mill that produced this. The mill test reports produced by a different company may look a little different. In this case, it says that the delivered steel qualifies as Japanese industry standard SN400B. The sheet gives the tensile properties and the chemical compositions, which were the basis to judge that it qualifies as SN400B. Also gives the name of the company, I'm sorry, it's trimmed out, and the name of the factory that produced the steel. This information is required for quality control. Now, we do have statistics on where the steel are in yield strength and tensile strength against the minimum and maximum limits. This is where we are. For this SN400 steel, the minimum yield strength is 235. The maximum is 355. So if you collect data from the mill test reports, we obtain this bell shape, the expected Gaussian distribution. For this SN400B, you might notice that the bell shape is trimmed here. This is because a small portion disqualified and did not make it to the market. Now, among the schemes that are adopted for quality control is this fabricator certification. Actually, it's not all, but most, the vast majority of steel fabricators earn this certification. There's a grade J, R, M, H, S, and S is for probably super, is the highest grade. The number of fabricators we have is something of around 2,000, and only 1% of those 2,000 qualify as the super grade. Now, S is probably for super, H is for high, and M is for medium. Now, the primary difference between these are the grade of steel that they are allowed to deliver. The lowest J grade can use the most standard steel and only to 16 millimeter. If you go to a grade H, you can use higher strength grades and to thicker. Now the super grade can use any steel. Okay, so this way, the certification is done by looking into the number of the welders that meets the qualification to do the thicker work, and the extent of quality control or the quality control management that is in place in the fabrication shop. Now, this is interesting. This photo has historical significance. What this is a one-to-one drawing of the connection that is drawn on the floor. This is probably the floor view of the column and the beam connecting into this, and very straight lines. This is really drawn one-to-one, and if you go to steel fabricators in Japan, you might come across a room like this, typically in the roof floor of the shop. probably 30 years ago, this floor was full of a chalk drawing, so that the engineers could come um, to discuss the detailing of connections and the complicated arrangements of the steel work. Oh, maybe you're wondering, yes, this is old-fashioned. These days, everything, of course, has been replaced by AutoCAD or computer-aided design and looking at the monitors. Sometimes because this floor area is available, they would print the drawings one to one and spread it on the floor. But otherwise, this tech room is historical. Okay, I mentioned that all the primary welds, or most of the primary welds in Japan, are done by gas shielded middle arc welding. I'm not aware of any other country that does this, but this is different from. I know that in Europe and in the United States, flux core arc welding would be the primary type. I don't know what it would be in India. Well, this is a type, a semi-automatic welding that the wire is being fed as the welder is welding, and simultaneously there is shielding gas that is shooted around the electrode. The shielding gas is a mixture of carbon dioxide, maybe not entirely good for the environment, but carbon dioxide and inert gas such as argon and helium, such that the molten weld is secluded from atmosphere, especially oxygen. Hey, please keep note that this is the choice of welding process that is favored in Japan. The same gas shielded middle arc welding is done in the fabrication shop or in the field. Okay. The quality of welding is controlled in two ways. One, by licensure. All welds must be completed by welders that have the right license. And the license is classified by the plate thickness, the welding procedure, the groove geometry, and whether or not backing is used to complete for the butt weld, and the welding position, flat, vertical, or upward. Okay, so there is license for simple welds and all variety of more difficult welds. And welders need to have the right license to complete the welds. And there is a record kept on who, with what license, made each of the welds. And of course, a license is required for the weld inspectors. Now, the second scheme for quality control is the inspection. Okay, all columns and girders are checked for quality control by ultrasonic testing, as well as visual and by direct measurement. The sections, dimensions, and the length, especially of columns, are measured, and I believe they have to be within 2 millimeters. Otherwise, they cannot be delivered to the construction site. And look at how these beam stubs are welded to the column. The squareness is also very, very important. So at this point, you might be wondering, okay, Japan is earthquake prone. The beams and columns, they may go to plastic deformation. And knowing that, we are placing a lot of welds right where we expect plastic deformation to happen. That is very true. We recognize that. But this is the favored fabrication procedure. And we are aware that quality control is very important. Now, moving on to how buildings are actually constructed. I'm putting together the information I've discussed so far, and with more details to walk you through how buildings are constructed from steel from the mill through the fabrication shop to the erection process. I mentioned that there is certification for fabricator. For ordinary buildings, probably the RMH grades do the work. The J grades are quite limited, so that they would build only a simple structure. As indicated here, the floor area cannot exceed 500 millimeters squared. So they are very simple structures. So what we call buildings would be constructed by this RM and H grades. This is the same slide I showed you before. For ordinary buildings, the columns would be cold formed HSS. The beams would be rolled sections. The columns will be diced up, and the diaphragm plates will be inserted. Lots of CJP welds to form the columns, as well as to connect this beam stub to the column. Automation or robotic weld is implemented to the extent possible. In Japan, we call this type of beam to column connection detailing the through diaphragm connections, because the diaphragm penetrates the column or penetrates through the column. Okay, we know that mechanically or from the viewpoint of structural performance, putting a lot of welds here is not ideal, but this ends up being the more simple fabrication process. Now, these cold formed square tubes are formed by bending plates. We have two types of cold formed square tubes. One is BCR. I believe in English literature, this is termed the formed from round. The plate is first bent to form a round section, and then the round section is welded to close the section, and subsequently the round is pressed from four sides into the square shape. Now, this process ends up cold forming the entire section. Yes, the corner is formed more, but the entire section is formed. The second process is, well, we call this type of tubes the BCP, but this is formed by the form square weld square process. The plate is formed. If the column is not too big, it's bent 4 times. Bent 4 times for 4 corners into the square shape, and a big weld is placed to close the section. If we go to very thick plates, we would rather bend these plates twice and join by 2 welds. Now the BCR, the upper one, is favorable to smaller sections, and BCP, especially the lower forming process, is better for bigger sections. Now, these are the 2 primary types of sections that we use for columns. Now, to form the column tree, we first dice up the column and start from this short part. We see 2 weld beads here and here, so this must be a heavy BCP section. At the 2 sections, there is groove prepared, a groove of 60 degrees prepared, and there is backing placed. The same is done to the other side. Okay, the backing is looks like this. We have these perfect backing plates. Their size, they perfectly match, wrap around the corner and match the section. Let me go back one step. So probably it needs to be cut to adjust the length, but otherwise it wraps around the corner nicely, so that we have continuous backing through around the section. The backing bar is attached by tack welding, and this fabricator is also welding these slits to stiffen up the backing bar. Now, such a short segment of square HSS is attached to two diaphragm plates. The backing bar is hidden here, but we see the root of what's going to be the groove weld. There's another tack weld attached to connect the backing bar to the diaphragm plates. Now, this groove, these two grooves between the short HSS and the diaphragm plates are going to be completed with CJP groove welds. Oftentimes, this is automated. These closed sections are favorable for robotic welding because you might see that this table has the shaft so that it circulates. As the column is rotated, the robot only needs to make sure it is following the groove. And the rate is controlled so that the weld may be placed continuously without overheating the weld. Okay, so once this piece, which we tend to call the dice, formed by the short HSS and diaphragm plates, this is done. This is the first CJP weld completed, so this needs to be inspected. It makes sense to inspect at this stage because we don't want to find problem after everything is assembled. Okay, inspection is done here. Afterwards, the beams are coming in. The beams are cut by bandsaw. And if there are bolt holes, the bolt holes are drilled. And this same machine that drills bolt holes also prepares the groove and the weld access holes. Yeah, you might notice this is a rotating blade, which is placing the groove at the top and bottom flanges simultaneously as bolt holes are being drilled. Okay, the short beam stubs may look like this. Okay, the side closer to the bottom right is going to go to the column, and the part farther apart will be bolted to intermediate beams at the erection site. Okay, such beam stubs. Okay, this is another view of the similar machine that prepares the groove and the weld access hole. The weld access holes, as well as the groove, are completed by a set of blades. Okay? There are two tables on the left-hand side and the right-hand side. These guys go up and down to complete the weld access holes as well as the grooves. Okay, the short beam stubs may look like this or this. Now, in the old days, there was always a weld access hole to complete the CJP groove welds to for the beam flanges, but more recently, the fabricators are comfortable with completing the beam to column connection without weld access hole. Now, this is possible for a couple of reasons. One, this piece is being fabricated in the fabrication shop so that the CJP groove welds can always be placed continuously from outside. Okay, if the welder needs to complete the welds in the fixed position, they have to place this weld from above. But the welder only needs to flip this piece upside down so that he or she can complete this weld from outside. Oh, until the 1995 Kobe earthquake indicated problems of the weld access holes, people started shifting to removing the weld access holes entirely. So probably nearly 90% of the larger fabrication shops would be adopting this no weld access hole procedure. It would look like this. Okay, the beam connected to the column, the beam flange to the diaphragm plate, beam flange to the diaphragm plate. There's backing on the inside of the beam flanges, and we have no weld access holes. There was no weld access hole from the beginning. Okay, this is done by using the backing bars that are split at two sides of the web. This backing bar butts against the beam web. Now on the other side, there's another beam backing bar that butts against the same beam web. That way we have a continuous backing bar, such that the CJP groove weld from outside can be placed continuously. Okay, there is a lot of weld that are overlapping each other, but we have established that this overlapping of welds is not going to cause problems to the seismic performance of these connections. Okay, after completing that column dice piece, the welder may be attaching these beam stubs one by one, typically from four sides. Okay, I'm not going to complicate today's discussion too much, but you may wonder, why are there more than two diaphragm plates? It is because the beam connecting at the same location may not have the same depth. It may not connect at the same height. Okay, these three beams connect at the same height, and they seem to be same in depth, but maybe the beam connecting from the other side meets this diaphragm and the bottom diaphragm. Now, this complication happens quite frequently. Okay, this is the completed piece. The column dice piece with, in this case, four diaphragm plates with beam stubs connected from four sides. Now, this small piece is connected with the rest of the column. Okay, what this welder is doing is that he is matching up the dimensions nicely. Now, because the column is made up of many pieces, it's very important to line up everything. Line up to level, line up to squareness, and line up to the exact length. Now, this is quite a difficult procedure that requires a lot of experience, because we are putting many welds along the length of the column. So that once the welding is completed, the column typically shrinks by several millimeters. but the required precision in length is in the 1, 2, or 3 millimeters. Fabricators have established from experience, based on the number of welds and the thickness of the column, you need to start up with plus how many extra millimeters when you're assembling the pieces. Okay, you may notice the groove prepared to the column. The weld is not made yet. This is a process of aligning the pieces together and then tack welding before the big welds can be placed. Okay, the big welds are typically done by the robots. Okay, we have one of that connection piece with many beams coming in a second one, and there may be a third one outside of the frame. Okay, I didn't bring video today, but this column, this machine rotates the column as in this case there are two robotic torches. Just needs to follow the groove. And of course, at this stage, the inspection is done. Now, if you go to a steel fabricator in Japan, there will be many of these pieces. So each of, big pieces may be priced as something of, I'm sorry, I cannot convert to Indian rupee, but in US dollars, the big pieces will be priced to something like 30K or 50K in US dollars. A lot of work, a lot of steel, but a lot of work. Now, there's not much to talk about for the beams, but there shouldn't be much to talk about beams, but sadly there are, because there tends to be many stiffening and many holes. For bracing connections, the bracing connections might be done like this. Okay, the bracing connections may need to go to the column as well as to the beam, so that it's good to extend the beam stub a little further, so that the gusset plate or the bracing connection fits within the column tree. Now the base plate might look like this. The columns are very critical components of a steel building, especially if they are expected to go through earthquakes. I already mentioned that any weld that goes to the columns needs to be, any welds that goes into splicing the columns, they have to be CJP groove welds. And the same applies to the column base. A big column base plate, you might wonder why is this column base plate shaped in this very peculiar way. This is because this base plate is a part of a proprietary product. I'll talk about this after a couple slides. Now, such piece is brought to the construction site. These column trees are connected vertically to each other and horizontally through intermediate beams. Okay, this is a different photo to better illustrate. Okay, we see column pieces like this. They are transported by trucking like this. I want you to notice that there is definitely a size limit for the trees of these columned trees. They cannot be too long, so that typically they go up to 3 stories tall. And the beam stubs sticking out cannot be too big, because otherwise they will exceed the width of the truck. Now, the columns are connected vertically to each other, and in between we have the intermediate beams. And the intermediate beams are bolted to the column trees. The bolting requires many structural bolts, high-strength bolts, and they have to be fully tensioned. If they're not fully tensioned, if they're slipping, you don't expect a good bending moment resistance. Now, the splicing after completion will look like this. Now, the column splices are typically done through a procedure like this. This is the lower column, and the upper column is going to come into the picture. And in the erection site, they typically attach these jacking system so that they can correct the angle or height over the floor to finalize the position of the columns. After these, the position is locked, again, there's another CJP groove weld. This time, this is done in the erection site. This is field welding, but not a huge deal because unlike the connections to the beams, the welds made to the beams, the CJP groove welds for the column splicing is typically is easily done in a controlled environment. Okay, so that concludes the big part of today's discussion on how typical steel buildings in Japan are erected in Japan. Hey, let me summarize. The primary pieces would be the column tree and the intermediate beam portions. I emphasize the fabrication of the column tree because there's a lot to it. A lot of welding and a lot of quality control. Now, I thought it's worthwhile to mention a little bit about column base connections. In Japan, we say that there are 3 different column base types. One where the base plate is exposed above the foundation. The second type, the column base plates will be further wrapped around reinforced concrete. If you wrap the column base with reinforced concrete, you can stiffen up the column. Another method to stiffen the column is to embed the column base inside the foundation. This would typically mean that the column base plate will be buried in a deeper part of the foundation, and after the base plate is anchored, the upper part of the foundation will be completed, will be filled with reinforced concrete. Anyway, the encased method and the embedded method requires a lot of additional work. Therefore, the vast majority of steel buildings, unless there's a basement, or the vast majority of steel buildings that do not have basement will adopt this exposed column base. There's a lot of thought that has gone into how to design such exposed column bases. Especially because we have seen a lot of evidence of damage. After the Kobe earthquake, typically heavily damaged buildings means that there was damage to the column base. Therefore, we now have a set of detailing rules for column bases. Okay, the anchor rods need to have a certain length, and there has to be sufficient anchoring. Definitely, the anchor rod has to have double nuts to prevent loosening. But there are other considerations beyond this. Looking at the possible failure modes or the load resistance, we expect compression to be delivered through bearing against the foundation. That's fine. But when there's bending moment, we rely on the anchor rods to resist, that help substantially in resisting. The anchor rods are also expected to bear against the foundation to resist shear force. But by far the most important is what to do with the tension delivered to the anchor rods. Typically, these exposed base plates are designed such that, but by viewing this green section as a reinforced concrete section. The issue is how to develop these anchor rods. The failure modes may be categorized into these, but there are favorable ones and non-favorable ones. Okay. The favorable ones would be these three, because the ones that I crossed, this one's also bad. Fracture is definitely bad, but anchor failure and crushing failure and pull-out failure, they are very non-ductile. Bending of the base plates is probably good, but this is not chosen in Japan. So engineers either choose to yield or form a plastic hinge in the column, or to allow the anchor rod to yield and extend. Okay, if you allow the anchor rod to extend, you tend to see a moment rotation relationship that looks like this. What's happening is that if you rotate or bend the column in this direction, you extend, in this case, the left anchor rod. If you come back, there's no resistance until the column is deformed back and the other anchor rod starts picking up tension. You repeat this a couple times, then the anchor rods will all be extended like this. You might notice that there is no moment resistance in this system until the base plate rotates enough to engage the elongated anchor rod. Therefore, we start seeing what we see, this slipping behavior in the hysteresis. Okay, there is good ductility in this in such behavior, but we have to make sure that this anchor rods behave in a ductile fashion. If you take a close look at these anchor rods, you might notice that they are not your standard rod. First of all, they are not fully threaded. Second, the shank has a bigger area than the threads, or than the threaded portion. Okay, so let me explain that first. So right now, since about 10 years ago, we have these special anchor rods that should be used for exposed column bases. The more ideal one is this cut thread one. No, I'm sorry. The more ideal one is this other one. This is formed in a special way. The threads are formed such that the minimum area of the thread is not so much smaller than the shank of the rod. Okay, typically the thread is machined so that the minimal area is substantially smaller than the shank. You cannot expect much ductility from such rod. To guarantee ductility in Japan for new construction, we tend to use this special anchor rod. Now, another concern is that if you're an engineer, you may not like this such moment rotation behavior. And on top of that, if you allow this anchor rod to yield, that means that the connection is weaker than the column. You might benefit from preventing the anchor rod from yielding. Place enough anchor rod so that the base plate connection is stronger than the column, so that, going back one slide, you form a plastic hinge in the column. That way you can form a much stronger first story. But remember, if you remember the many failure modes that you have to think through in a column-based connection, detailing the column-based connection is very cumbersome. So instead, some smart people went through a lot of thinking and a lot of testing to develop proprietary products. These proprietary column-based connections are quite popular in Japan. Probably a good half of exposed column-based connections now adopt some proprietary products. I mentioned this strange base plate. This is a cast piece. These cast pieces are cataloged for different column sizes, and they are sold or provided as with a set of detailing that goes into the foundation. The right anchor rod with the right diameter, right length, and a right anchoring method inside, or the bearing method inside the foundation. And in some products, there's also the right caging that goes inside the foundation. So if you choose to use one of these proprietary products, it's a no-brainer. You just look into your column size and look at the catalog and just pick up the right one. So hopefully you understand why these are gaining popularity. Now, let me move on to the last section of today's lecture. How are high-rise buildings constructed? This is a photo of a high-rise. Actually, I pointed this to Professor Ashwin Kumar when he visited Japan 3 years ago. This is right in front of the Tokyo station. High-rise of probably 40, 50 stories. A steel building. Square columns and deep I-section beams. And the I-section beams comes with a lot of holes. A close-up view, you might notice that the I-section beam has widened flanges near the beam-to-column connection. And a magnified view. Okay, the column is a square shape, but it is so big that it goes beyond what can be bent. These are welded, built-up column sections. We don't have that protruding diaphragm plate. Instead, it's not visible, but I'm pretty sure that there are diaphragm plates welded inside this big column. The beam flange is now welded to the column, and the weld must have been completed in the field. The beam web is bolted to the columns. I believe the shear tab is not clearly visible, but it must be through a shear sub, the shear tab. This is another high-rise building under construction. This is more recent, but this one surprisingly is using diaphragm plates. Now, this is an oddball, but the reason I chose this photo is to show this. This is what they have to do when the column grows smaller as you go up. Right in the panel, in the beam to column connection, this is an odd shape. The the cross-section of the column is growing smaller as you go up. And the transition of column dimension is done inside the connection. Anyway, the typical construction for a high-rise building is done like this. The column is built up by welding, and these big welds for thick plates are done by submerged arc welding. And in the connections to the beams, we need the diaphragm plates, and those diaphragm plates are placed inside this built-up column through electroslag welding. These are special big volume welds that meets the purpose. And in the field, we need to have the beam flange welded to the column by CJP groove weld. And the staging for the field welding might look something like this. Now, the pieces or the fabrication for high-rise buildings would be done by H, but the really high rises will be done by the S grade fabricators. You might notice that is because high-rise buildings tend to use higher grade, stronger steel and thicker steel plates. This is a photo of the built-up column shapes being made by submerged arc welding. Submerged arc welding is a big volume weld, and you can see after probably tens of seconds after this big weld is placed, the molten weld remains red. As a matter of fact, I think there are 3 torches going into simultaneously to place a big weld. Submerged arc welding is a special type of weld that places a flux of a form of sand and dips electrode inside the flux. The equipment is so large that it has to be guided by railing. Now, this type of welding procedure is very well suited for big volume welds that travel straight. This is a different fabricator that shows the equipment. You might see the flux, the sand-like flux, and the torches. I think this is 2 torches sticking in simultaneously. So after the weld is completed, it might look like this. And if the weld exceeds a certain size, it may take more than 1 shot to complete the entire weld. The weld is started and ended outside of the primary section, and this part sticking outside, this is actually runoff tabs. This part will be torched off and not used in the building. Okay, these diaphragm plates are serve temporary purposes so that the plate does not distort during and after the welding as after the steel cools. Now, where the beam comes in, we need to place the interior diaphragm. The interior diaphragm is placed by electroslag welding. Electroslag welding, okay, I have never had the opportunity to take a photo of this being done, but this is done by pulling up the torch vertically. It's similar to electroslag welding that the torch sticks through flux, but it travels vertically upward. This welding procedure is very good for the purposes of placing the straight welds for this diaphragm plate. This is a diaphragm plate, and this is a diaphragm plate. There is backing at four sides of this at this side of the diaphragm plate, and there's another one at the other side of the diaphragm plate. Okay, four side backing at both the top side and the bottom side of this diaphragm plate. And the hole you see here, 1, 2, 3, 4. This is where the electroslag welding is going to be placed. And there's a vertical tunnel, and the torch travels through this tunnel. The photo on the right shows the plate, the plate that's going to complete this box shape. The submerged arc welding is going to come here, here, and here. And after that is done, the electric slag welding is going to come in to complete the weld for the diaphragm plate. Okay, after such big welds are done, the sear tabs will be placed. And these pieces will be delivered to the construction site. Now, submerged arc welding is also used to make built-up beam shapes. Okay, these are built-up eye sections. Some are widened at the ends to achieve better seismic performance, like here. Another example of the beams with has widened flanges at the ends so that the connections can perform better against earthquakes. This can be done for built-up shapes because the beam flange and the web and the other beam flange, they're all cut off from separate steel plates. Okay, this is an example of a column that is completed at the fabrication shop. Okay, so a column, and they decided to place a through diaphragm plate here, here, here. In other cases, they would use interior diaphragm, but there are many varieties. The short segment where the column changes in dimension is where the beams come in. These columns may have circular holes in the diaphragm plates or all plates inside. The reason for these holes is to allow concrete to go through. So the Japanese adoption of square hollow shapes for columns give good opportunity to convert these columns into CFT, concrete filled tubular shapes. Okay, again, beams may come with many attachments and many holes. It's sometimes sad to see these. Now, these pieces are delivered to the construction site. The column is running up vertically. The beams are delivered, and they are connected. First, the web is connected to the column, and after adjustment, the bolts of the web are fully tightened to start placing the CJP groove welds for the top and bottom beam flanges. This is the same photo I showed earlier, showing how the welder may be working at the construction site. It's required to provide him or her a good footing and to shield the environment from rain or wind. This is very important particularly because of the type of welding that we use. This is a gas shielded weld that does not use flux. So if the wind blows away the shielding gas, you cannot expect a good quality weld. The good footing is also required for the inspector. Okay, to wrap the discussion for high-rise, typically the columns are a piece of its own. It does not come with a beam stubs. It will come with the shear tab, but not with the beam stub. The column is delivered as a column. The beam is delivered as the whole beam, and they are connected at the construction site. That this procedure requires field welding. So I hope I was able to emphasize the substantial difference in construction type between regular buildings and the really high-rise buildings. Okay, a couple of additional remarks on what happens in the foundation. Typically, high-rise buildings have basements so that the column extends into the basement. In such case, the first floor will be supported by a grade beam, and the column will go down further. And very typically in Japan, the columns of a steel building that goes into the basement floors will be made composite. You might notice that the column is no longer square shape. It is an I section. No, it's not an I section. It's actually a cruciform section. The cruciform may be more clear here. It's a cruciform with flanges at all four tips. And this column will eventually be wrapped around reinforced concrete, either to be part of a steel wrapped around or steel encased reinforced concrete composite section, or a composite wall. I think in this particular project, it was a mixture of the two. This part up here is wrapped around column, and the columns here seems to be part of a composite wall, as seen here. Okay, so let me wrap up today's lecture with major points that I wanted to communicate. Okay, the popularity of steel construction in Japan is supported by a very large selection of steel, both in material, grade, and size, but also through a very very close attention to quality control. Our columns are predominantly square tubes. For regular structures, they are cold formed shapes, but for big high rises, they'll be welded, built up boxes. Okay, we try to complete as much of the critical welds, especially at the beam to column connections, in a controlled environment. This is because our seismic design typically require fully welded joints at these critical connections. Okay, the column tree construction is very typical, but the column tree works only to a certain size, because if the column and the beam grows too big, the column tree size combined will exceed what can be transported by the truck. Now, quality control is crucial. I cannot emphasize this enough, because the particular construction procedure we adopt ends up placing many welds in critical connections, particularly along the columns. Okay, I hope I left enough time for questions, but I thank you for your attention so far. Thank you. I will stop here and open for any questions if we have received so far, anything so far.
Thank you, sir, for such an insightful lecture. And yes, we do have a question.
Mhm.
Yeah, it is which methods are being used for weld inspection in Japan? At
Uh-huh.
beam column connection, why are okay, it's a two-part question.
Okay.
At beam column connection, why the flange of a beam is welded to the column and web of the beam is bolted to the column rather
Mhm.
than everything bolted?
I see. I see. Okay. 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 The first question. Okay. I don't. I'm not. I don't have license for weld inspection, but 100%, no exception. All CJP groove weld needs to be inspected. I believe the requirement is the same anywhere in the world. This is because CJP groove welds are required to fully deliver the force that the base metal can develop. And they are used at very critical locations. Now, this is an example of weld inspection. The biggest element of weld inspection is the ultrasonic testing to pick up any defects. There's a rule that specifies the maximum defect that is permitted. Okay, if there is a defect or void, or any defect, that might be inclusion, but any defect will be picked up as a void or a crack or air crack inside inside the weld. And the size, if it exceeds a certain size and limit, then the weld must be removed until the defect is found and removed, and subsequently the weld might have to be repaired. Okay, so that's the most important inspection procedure. But on top of that, there's the typical weld size gauge to make sure the weld is made to the required geometry. And the weld is also, I mean, there are items, I don't have the full list, but there should not be undercut or, I think undercut is another concern. Okay, so there's both ultrasonic inspection and visual inspection that's required. Okay, I hope that answers question number one. And question number two is, why don't we use fully bolted connections? So one point in history, all steel framing was done by riveting. So I believe that a direct evolution after riveting was all bolted or heavily bolted construction. Now, why? Okay, why this particular type of construction is popular in Japan? I believe the reason is because it serves quick erection. The fabricators are placing a lot of welds, so this fabrication work is more expensive, but because everything is made to precision and right now, typically in Japanese construction, we use the twist-off bolts so that tightening the bolts is quite quick. So combining everything, the steel erection is very quick, and that is one major advantage over our reinforced concrete construction. I'm sorry, I'm not sure if that was sufficient answer to the second question, but how about that?
There's another question on do you use fire resistant steel, or rather, is fire resistant steel used in Japan?
Fire resistant steel, I think one of the early ones were invented in Japan, and it serves a certain purpose. There's a a law requirement in Japan that the steel column has to sustain load for a certain amount of a certain degree for a certain duration of time. So there's a standardized test, and there's a grade of steel that meets that qualification. Fire resistant steel, I do not think is all that common. It's not sold in abundance. Certainly, fireproofing is the most common option. Maybe okay, but there are places where we don't want to use fireproofing, and that would be where the architect would want to expose the steel. The first choice would be to use fireproof painting, but I think it would be a cost decision of cost whether the fireproof painting well, meets the requirement cheaper, or the fireproof or fire resistant steel meets the requirement cheaper.
Another question is on the material that you earlier mentioned, that what are those wrapping materials used for fire resistance in high-rise buildings?
Oh, wait, maybe I did not notice. Let's flip through. I do not. Okay, this one, this before fireproof. Okay, I may not have the wrapping, a photo of the wrapping, but I think it's increasingly for recycling purposes. The foam type fireproofing is very painful to remove, so that from environmental concerns, the wrapping type that can be stapled to steel is gaining popularity. I'm sorry, I'm not very knowledgeable on the wrapping fireproof.
Another question is, in beam column connection, why web of beam is bolted at connection, because there was not an angle section connecting beam web to column.
Um,
I'm not sure.
okay, here, yes. So in high-rise construction, I suppose, I mean, for example, maybe I know that the American construction requires to always use weld, I mean, always weld the beam web, but that requirement does not exist in Japan. For example, this one is not using a whole lot of bolting. Maybe, I mean, the reasons I can think of is that this beam is actually designed to be a floor beam, although it is welded. But actually, this one also does not use many bolts. Maybe this is so long so that the shear force is not substantial. But the question is why? I'm sorry, could you repeat the question again?
It is in beam column connection. Why web of beam is bolted at connection? Because there was not an angle section connecting beam web to column.
Angle section. Okay. Okay. This is not okay. This is an example of the shear tab connected to the column. And in the construction site, the beam web will be connected to the shear tab, and the beam flange will be welded to these diaphragms. So we are not using angles. We are using shear tabs. This, okay. I'm not sure if that answered the question.
Moving on to the next question. How the length of the column tree stub is being designed?
The length of the columns.
Column tree stub.
Okay, column tree stub. Okay, maybe. Okay, are we talking about this piece? This length is dictated by where the beams come in. The location of the highest top flange and the lowest bottom flange. Now, this arrangement is not ideal, but a beam stub. Oh, a beam stub. Okay. I understand. The beam stub. Okay, the question is, how is this length determined? Okay, if you think about what is ideal, the ideal would be the location that sees minimum force during regular hours. It is our understanding is that the ideal location would be the inflection point under gravity loads. That would be something like 1/8 or a little more of the beam span away from the column. Now, that is the ideal location, but I think the rule applies everywhere. We need to pursue efficiency, convenience, and economy. And that is dictated by, where do I have it? What can be put on the truck? If this beam stub is twice as long as what's being placed on the truck right now, it cannot be transported. Or even if it can be transported, they can load only one piece instead of two. Therefore, at the end of the day, the typical length of the beam stub is measured as 1 meter from the center of the column. That's quite typical. Okay, thank you.
Okay, another query from one of the participants is how the whole steel structure is grouted to ground, or is it done by concrete foundation?
Okay. That is okay. I don't have a photograph of that, but there is a lot of precision that goes in there. The column base is all leveled by a close, accurate surveying, so that they would typically align the top of the column base plate to be at even height. So I don't know what would be most ideal. Okay, let me go back to this. Okay, this arrangement. I think that, it's done similarly in most countries, but after everything is placed, they put non-shrink grout between the foundation and the base plate. This also means that until that's done, there's gap. The gap is needed because it's not visible after the grout is made, but there is a nut inside. I think it's called a leveling nut. So that using the leveling nut, they can adjust the rotation and height. And after that adjustment is done, the non-shrink grout is placed to really lock the position. Oh, I hope that gives an idea that there's a lot of a thought for precision that goes on to leveling the foundation. And the leveling is done to the base plate.
Okay, another question is diaphragm can be created from outside without cutting sections? Can diaphragm be created from outside without cutting
Okay, okay.
sections?
That's an interesting question. And I mentioned that today I mentioned that there are two primary types of connections in Japan. One is the diaphragm plate protruding the column, one that the diaphragm completely inside the column, and there is a third type where the diaphragm plate is welded outside. There is substantial research that goes into that that has established a design procedure, and it has been used, but it's not catching popularity. I think one of the reasons is that maybe let me try to. I'm sorry, I don't have a photo of that. Okay, so maybe this one. This is a case where the diaphragm is protruding the column. There's another way to weld a diaphragm plates. It would probably look like this around the column. Okay, and this is my understanding of the scale of this. In Japan, we call this the exterior diaphragm. This diaphragm plate has to be of substantial size. I think that there will also be like this. Okay, it has to be substantially big and substantially thick to provide the stiffening effect of the column. And also, we don't want this to be so big, but if you squeeze this too much, we end to fail here. So that is what I understand from the research. We do have this exterior diaphragm option, but probably because this exterior diaphragm ends up being big, it's not gaining popularity in Japan.
Another query is, can you please explain the benefit of the proprietary column-based connection?
Okay. Yes. This one. Okay. The whole point is that if you are to design this on your own, you have to check at least, I mean, all these limit states, and it can be quite cumbersome. And if you have 4 different column dimensions at the first story, you have to design for all of them. And this column-based design will also interact with your foundation design. Okay, so if you can imagine the many iterations that's involved with designing something like this, you can just pick a product from the catalog. And I think that the market is competitive enough so that this proprietary option is not too expensive. But I also recently visited a fabricator that said that, okay, they came up with something that looks close enough to this proprietary product.
Okay, how can we minimize the risk of brittle failure of high-strength steel in high-rise building?
Okay, so that's something that I didn't discuss at all today, but there are 2 things that's being done in Japan. One is that there has been very extensive study on the toughness of steel and measures to for quality control of steel. Now, let me go back to that table. Oh, wait a minute. I'm good. I hope this is visible. So if you weld to high strength steel, there is higher grade than this, the highest grade has a yield strength on the something like 600 Newton per millimeter square. But if you go that high, it's impossible to find a weld electrode that matches that grade. So in that case, the current guideline is to make just a very big fillet weld. Okay, that's one thing I can say. Second thing is that for this SA 440 with a yield strength of 440, this is used very commonly for high-rise buildings. And for this one, there is a matching weld electrode. And including such weld product for a high-strength steel, there has been extensive study, and there is a quite severe Sharpie requirement to qualify for use in seismic applications. Now, the last thing I can say is that something similar to what's been done in the U.S. and Europe, there has been a series of qualification testing. And what the concern for high rise is more the number of the very big number of cyclic loading rather than big deformation. And we have this established fatigue rule to check the safety of welded connections for high rise buildings. So that's my short answer to what can be easily be a series of lectures.
Shall we take one last question? Okay. Are there any stresses generated in the steel during the bending process, specifically in reference to the fabrication of curved built-up sections?
Yes. That is okay. That is a big problem that the Japanese construction industry or the engineering community has overcome. Wait a minute. Where's that? Where is that? Where did I show that? I'm sorry. I forgot where I. Okay, here. Yes. Okay. 99%, maybe not. That's too much. 95% of steel buildings in Japan and 99% of office buildings in Japan use this BCR or BCP. These products are made by cold forming, and yes, the effect of cold forming is substantial at these corners. But about 2 decades ago, there has been a lot of testing done for the columns itself, and also for the beam to column connections to establish that even with the altered properties at this corner, these columns perform good enough. These columns are still designed with penalty. They're penalized with a reduction of strength when they are proportioned. And we have a strong column, weak beam requirement, so that the action on the columns would not be too big, so that we expect column hinging everywhere. Now, what happens with cold forming, especially at this corner? As I write here, the radius is 2.5 or 3.5. The outer radius is 2.5 or 3.5 of the thickness. Now, this is quite substantial bending. What happens is that you strain harden the material, but you also there's also the aging effect. Aging is that as after you plastically deform the steel, there is a further increase in strength and loss in ductility with time. The aging saturates after a couple of months, but there's this dual effect. that exaggerate the strain hardening. We recognize, but we confirm from testing, and we do impose requirements so that these effects do not grow to be too large. Okay, I hope that answered the question.
Yes, sir. Thank you so much. And for today, we won't be taking any more questions, but the remaining questions we shall be sending to Professor Okazaki so that he may please find time and answer them. And thank you, sir. We've received a lot of appreciation from our participants today regarding the lecture. They've really found it insightful, educating, and I would call it an excellent lecture. So I would again like to thank you for finding time for the webinar.
Oh, the pleasure was mine. I'm glad I got the chance. I mean, these things are always better in person, but hopefully in some time in the future. Then.
Yes, yes. In future, again, we would hope that we can have some more lectures from you.
Okay. Thank you very much.
Thank you so much, sir.